Okay, good morning. Welcome to Introduction to Photonics. So, in our last lecture, we were talking about finding ways to manipulate light, properties of light. And before we did that, we said, okay, let's first understand how light propagates through a medium. So, we went through this mass spring model and came up with a picture of how the permittivity or how does a medium respond to a incident electromagnetic wave. So, the response we saw could be complex in nature, and it is also something that is frequency dependent. So, we identified that the real part of the permittivity which provides the refractive index of the medium is not constant, and it goes through certain resonances, and at those resonances we saw that the imaginary part actually becomes maximum. So, that provides absorption in the material. And then we went on to look at what are the ways, possible ways that we could manipulate light that is propagating through a medium. And the first one that we were considering is polarization. So, we went through just a brief introduction of what polarization of light means, that we could have linear, circular or elliptical polarization, and then we took the example of two crossed polarizers or rather a polarizer and an analyzer which is rotated around its axis, and we said that actually goes through a cos square function. The transmitted light goes through a cos square function with respect to the rotation angle, and that is what we call as Malus law. And one example of this where this could be useful, we said, was in liquid crystal displays, and we said liquid crystal displays are such that when you apply a voltage, it rotates the polarization of light, and then your analyzer could be set such that the rotation corresponds to maximum transmission. Right. So, initially you may not have any transmission, but upon a voltage to this liquid crystal cell, you could rotate the polarization and you can maximize the transmission. So, you can turn light on and off in a voltage controlled manner with this principle. So, we will move along today, and we will consider ways of manipulating the polarization of light itself. So, let us look at how to change the state of polarization of light. So, is it possible to convert, say, linear polarization to circular polarization, or can we rotate the polarization of light? So, if you have a linear polarization at a particular angle, can you actually rotate it to 90 degrees and so on? So, how to change the state of polarization of light? To do that, what we need to consider is a birefringent medium. So, what do I mean by a birefringent medium? So far, in most of whatever we have considered, we said that our the response of the medium to a electromagnetic wave is isotropic in nature. So, what does that mean? If it is isotropic, then if you say this is Nx refractive index and this is Ny, for isotropic medium, Nx equal to Ny and equal to Nz if Z is the direction of propagation, So, the refractive index is the same everywhere. but a birefringent medium is actually an anisotropic medium, in which case Nx is actually not equal to Ny. Okay. So, when Nx is not equal to Ny, the light that propagates through that material, depending upon the polarization of the light, whether it is oriented along the x direction or y direction, it is actually going to go through a different phase change, or it is actually going to go at a different velocity, right. So, what happens in those cases? There is some interesting propagation principles that we can study with this sort of material. So, if you go back and look at once again an isotropic material, say this is along the x direction. So, x and this is y direction, and if we consider the refractive index, the refractive index is uniform everywhere. So, that refractive index we can call as N naught, NO. Okay. And in this sort of a case, if we consider a wave vector like this, okay, a wave vector will be supported by certain electric and magnetic fields, right. So, let us say the magnetic field is perpendicular to that. So, the electric field will be perpendicular to both the magnetic field and the direction of propagation. And if you consider the displacement vector, which is epsilon times E, that will also be in line with the electric field. So, both of them are parallel to each other, and in this sort of a case, if we look at both the k vector as well as your pointing vector. Your pointing vector denotes the direction of energy propagation, right. So, the k vector and the pointing vector are the one and the same. That is what you have been looking at all along in electromagnetics and so far and photonics also. So, they are all lined up with each other. Okay. So, this is for a isotropic medium, but when you consider a anisotropic medium, okay, the refractive index is not the same everywhere. Okay. So, the refractive index would be different along different directions, okay. And it may be along one direction, it may be with the same refractive index as the other case, but in the other direction the refractive index is different. We call that Ne. Now, in this medium, if you look at, let us say the let us say still once again the magnetic field is like this, and if you look at the electric field, let us say is like this, but when you look at the displacement vector, the displacement vector depends on the relative permittivity of the material, okay, along any that particular direction, and that relative permittivity gives rise to the refractive index of the material, right. So, the refractive index is different, and as a result of which, because it's actually sort of an index ellipsoid that we have, the displacement vector is not parallel to the electric field vector, okay, because the response of the medium is different. That is the question. Sorry, D? No. So, the question is, isn't the D independent of the material? D is defined as epsilon times E, right, and epsilon is epsilon naught epsilon r. Epsilon r is the relative permittivity, which is given by 1 plus susceptibility, and that susceptibility is proportional to the displacement. That is what we saw yesterday. So, D is actually dependent on the medium, the response of the medium. E is the applied electric field, but D depends on the medium itself. In this case, what is interesting is the k vector is given by D cross H. So, the k vector will be like this, okay, but your pointing vector is E cross H, E cross H conjugate to be specific. That pointing vector is actually slightly off. So, your pointing vector is like this, that corresponds to the energy propagation, whereas your k vector which talks about how the phase fronts are moving, the direction in which the phase fronts are evolving, that is different. So, this is a key point to note in an anisotropic material. In an anisotropic material, the direction of energy propagation and the direction of phase evolution is not the same, okay, may not be the same. I will come back to specific cases where they are same, but it may not be the same. The specific cases where they are the same is probably if you are going against the if you are going along the axis. If you are going along the axis, then you can say either the major axis or the minor axis, then you can say that both k and s are oriented along the same direction. But if it is going at some other angle, k and s need not be the same, okay, and that is giving rise to some interesting effects, okay, which is not so intuitive. So, one of the effects is, now we need to go back and look at Snell's law. Sorry, that is one more question. Okay. No, okay. So, it is talking about for Coulomb's force, it is dependent on epsilon, right. Yes, in the Coulomb's case, it is dependent on the medium, but the definition, electric field could be anything that you apply to the medium, right. Electric field is a independent parameter, that's your cause. The effect is D, okay. The cause could be because of the specific case where you are talking about in Coulomb forces, there are actually two charges that are interacting, and the force between them we define by the Coulomb force, and that Coulomb force may be dependent on epsilon, okay. Please do not confuse that with what we are talking about here. Here we are talking about an electromagnetic wave being the excitation, and the response of that medium is quantified through D, which is again quantified through epsilon r. Was there some other question? Okay. Okay, so let us actually revisit Snell's law. Okay, and we did not quite have this picture of Snell's law when we originally talked about it, but let us just look at this picture. Let us say you have light going from one medium to another, n1 to n2, and let us say n2 is greater than n1. So, in this medium, if I define the constant phase fronts, and let us say my normal is somewhere over here. If I define the constant phase fronts, then in this medium, that is actually a spherical wave front, right. If you have a point excitation, then the wave actually spreads out in a spherical manner, right. It's an isotropic material, right, this first material. And let us say to start with that the second medium is also an isotropic medium. So, in that case also you expect to have a sphere, but in this case the sphere will have a larger radius because n2 is larger, right. So, this wave the k value, the momentum actually is larger in that case. Now, if I have a wave that is incident on this medium at an angle, let us say theta 1, okay. How do you figure out theta 2? You basically say, okay, this is going to have a component along the surface, that's what you call as a tangential component. So, the tangential component on both sides have to be equal. So, which means that if I project this to the second medium, then you have where it meets this this constant phase front, right, that defines your theta 2. Okay. So, you write this as k 1 sin theta 1 equal to k 2 sin theta 2, okay, and because those represent the tangential components, and then that gives you sin n 1 sin theta 1 equal to n 2 sin theta 2, right. That is the Snell's law that we took up right up front. I said this is what we use across interfaces. This is what we use across interfaces separating isotropic material, right. So, that is okay. So, this is isotropic material. Now, consider the same for a anisotropic material. So, you still have n1 representing an isotropic material, but n2 now is characterized by two different refractive index, right. You can have n2O, which corresponds to an ordinary wave, okay, and you also have n2E, which corresponds to an extraordinary wave. Meaning, if in one direction it is seeing just an index an isotropic material, that corresponds to an ordinary wave, but now we have this other case that in the other direction it might have a different refractive index, and in that direction you would actually have this extraordinary wave come into the picture. Okay. So, if you draw the phase fronts once again, this is for the first medium, and then this is for the second medium along one direction, okay. But in the other direction you have a refractive index that is changing with respect to the different axis. Now, for that direction you have essentially an index ellipsoid that's defined by this. So, the index ellipsoid is such that in this case you have what is called the optical axis. The optical axis in this picture corresponds to the vertical line. Okay, it's the optical axis will be perpendicular to the direction of the extraordinary refractive index. Okay. So, let us say the optic axis is like this. So, my extraordinary index at this point is corresponds to NE. So, in this case, if you do the same thing that we did before, right, you have basically a wave that is incident to this material. So, you project the tangential components, you find that the tangential components, it meets this phase front at two different points in two different directions. So, in this case you have one wave that meets one wavefront in one direction. Okay, that we can call it as this angle we can call theta 2 O. Okay, but there is one more in the perpendicular axis. Okay, the perpendicular polarization sees a different medium effectively. Okay. So, if I have this polarization, it sees this normal medium, but if I have this polarization sees a medium which is birefringent, which actually has that index ellipsoid. Okay. So, that medium will satisfy Snell's law in a different manner. Okay. If you project the tangential components, then you have this angle which we can call this as theta 2 E, okay, which is also called the extraordinary ray. So, this is called the ordinary ray because it acts in the same way as you would expect any birefringent material to respond, any isotropic material to respond, that is called an ordinary ray. But the perpendicular polarization will actually correspond to this extraordinary ray. Okay. So, the orthogonal polarization will correspond to the extraordinary ray. Okay. So, you have one ray hitting that one wave hitting that interface, and that actually gets split into two waves, okay, each of them having a different direction. Okay. You understand that? Now, of course, if you have a case where the optic axis is like you take a material and you define the birefringence. So, you say okay, in this axis is N naught, in this axis is N naught, in this axis is N E. Okay. It is up to you as to how you cut that material. So, the optic axis is defined, and then depending on how you cut that material will have an interface like this. Now, to give you an example, you can cut the material such that that interface where you are cut corresponds to your optics axis. So, it's basically parallel to the optic axis, right. Both the optic axis and how you are cut are essentially parallel to each other. Let us see how things work in this case. In this case, you basically have your ordinary wave experiencing something like this, but for your extraordinary ray, that will be something like this, right. It will see a different refractive index, but in this case, quite interestingly, if you look at a wave that is going straight down, right. If you have this condition, your extraordinary ray will be aligned with your ordinary ray. Both of them are going through the same direction, because you cut your optic axis such that the extraordinary ray is actually passing through one of the axes of your crystal, okay. And so both the ordinary and the extraordinary rays, they go through the same, direction. They go through the same direction, but what happens in this case? What can you say about the speed at which light propagates for the two different polarizations? They will be different, right, because one is seeing this N naught and the other one is seeing NE as the effective index. Do you understand that? So, depending upon how you cut the crystal, whether you cut it along the optic axis or at an angle with respect to the optic axis. In this case, if you cut it at an angle with respect to the optic axis, you have a phenomena called double refraction, meaning you come in with one wave, but you go out with two waves, right. So, you have double refraction happening in this sort of case, whereas if you cut it across the optic axis, then you have only one direction of the wave, but in this case you have what is called retardation happening, meaning the phase between the two polarizations. Let's define the polarization. So, the polarization is such that your vertical polarization will be your ordinary ray, and your horizontal polarization will correspond to the extraordinary ray. Okay. So, here again this is your vertical polarization, whereas your horizontal polarization corresponds to the extraordinary ray, and that sees a different refractive index. So, you have retardation happening between the two polarization components. In the second case, if we have so you are asking if this is actually only for the, so the question is whether the direction would be the same irrespective of the incident angle. No, this is actually the direction for normal incidence. If you have for oblique incidence, you have to go back to this picture and then say, okay, where does the the tangential components, where does the momentum matching happen and you draw that line corresponding to that, you will actually find that it corresponds to two different points at which they meet. So, you will have double refraction for the case of oblique incidence. But in the case of normal incidence, and if the optic axis is aligned with the thing, so that the ordinary and extraordinary refractive index, they are different, but the orientation is actually the same, then you have this retardation. You do not have double refraction, but you have retardation. Now, you may want to ask, what happens if you have normal incidence, but your optic axis is at an angle with respect to the interface? What do you think will happen? So, what we talked about here is that the k vector will be aligned, right? The k vector will be aligned, so it's all normal, but your since the optic axis is at an angle, your energy direction, your pointing vector will be off axis. So, in the case where you have normal incidence and the optic axis not aligned like this, optic axis making an angle with respect to the interface, you would still see double refraction. That is actually not very intuitive, right? You say normal incidence, Snell's law tells me that I should have only normal beam going out, but because of the fact that for the extraordinary ray, your energy vector, the pointing vector, is not aligned to the k vector, right? You have phase fronts that are aligned in the direction of the original normal incidence, but your energy direction is off from that. So, you will actually see, if you see a dot through one of this material, right, you will actually see two spots. One spot, the center corresponding to the ordinary wave, and the other spot corresponding to the extraordinary wave, and you can actually rotate that crystal. We will show that in the lab today. You can rotate the crystal and you can see that extraordinary, the dot corresponding to the extraordinary ray will actually rotate. So, there will be one central dot which will not rotate, but the other dot will rotate. So, that corresponds to normal incidence, but you have a condition where the optic axis is cut at an angle with respect to the that surface. Okay. Now, let us quickly look at one example and then we will stop. So, based on this principle, based on this retardation principle, you can actually make components which change the polarization of light. Okay, that is what we wanted to look at. So, now you have let us say now what we are saying is, you might have Nx like this, Ny is like this. If Nx is not equal to Ny, then the polarization components aligned across the x and y direction, they are not propagating the same velocity. So, that means there is actually a phase retardation between them, let us call it phi, and that is going to be defined by 2 pi over lambda Ne minus N naught multiplied by how much it propagates, right. So, if you have, let us say, a material like this, right, and if you have a wave that is incident on it normally, and let us say the optic axis is like this, has been cut like this. So, we expect both the ordinary and extraordinary ray to go through this directly straight, but in this case they are seeing two different refractive index, okay, and let us say the thickness is d. So, as it propagates through this, it is going to accumulate a phase difference that is given by this. Now, for a given material Ne and N0, if you say calcite is an anisotropic crystal, now for that Ne and N0 are fixed, then lambda corresponds to the wavelength that you are coming in. By changing d, you can change the phase delay between the two polarization components. Okay. So, in this case what we are saying is your two polarization components are going to be like this. They are actually delayed. There is a phase delay between the two, okay, because of the propagation. They both come out in the same direction, but there is a phase delay between them. By changing the thickness, you can change the phase delay. So, for example, you can design it such that phi equals to pi by 2, okay. That is one thing that you can implement, right. So, you cut the crystal with a particular thickness such that phi equals to pi by 2. If phi equals to pi by 2, then what happens to the polarization that is going through? We talked about representing it as Ax Ex plus Ay Ey e power j phi, right. That is the general description of the wave. The incoming wave is linearly polarized, okay. So, the incoming wave is polarized linearly, but let us say it is at a 45 degree angle with respect to the crystal axis. Then for the incoming wave phi equal to 0, but for the outgoing wave you have Ax Ex plus Ay Ey e power j pi by 2. You have a phase difference of pi by 2. So, if you have a phase difference of pi by 2, if Ex equal to Ey and phi equals to pi by 2, what does that mean? That corresponds to circular polarization, and since phi is positive, you say this corresponds to left circular polarization. So, you came in with linear polarization, input phi equal to 0, that implies linear polarization, and you came in such that it is at 45 degrees. Why is 45 degrees important? The Ex and Ey components are equal in that case, right. So, this will be the case if theta equals to 45 degrees, right. So, this is what you call as a quarter wave plate, okay. So, a quarter wave plate, if you have a 45 degree polarization coming in, then it goes through that material, what comes out is actually circular polarization. So, linear gets converted to circular polarization. If you come back, that circular polarization, it is all reciprocal, right. So, that circular polarization will go back to the original linear polarization, okay. So, that is one thing. The other condition is if phi equals to pi, which you call as a half wave plate, because pi phase difference corresponds to half a wavelength, right. So, it is called half wave plate. If you have this case, then you have A x, the outgoing polarization will be A x E x plus A y E y e power j pi. E power j pi is minus 1. So, this is basically A x E x plus minus A y E y. So, whatever was the incoming polarization, whatever was the y component of the incoming polarization, that y component got flipped, right. So, when we look at that, so we will say that okay, if you have your x and y, let us say you have a linear polarization like this, then the x component remains the same, but the y component will get flipped, right. So, what you will have is a polarization that is, it will still be linear, okay, because it is not, it is just giving you a pi phase shift, right. That means it just flipped to one of the components. So, the phase difference it does not, it still remains linear, but it gets rotated. Okay. In this case, if what you will find is if theta is your incident angle, you will find that it gets rotated by 2 theta. The output will be rotated by 2 theta. So, this is actually you can call this as a polarization rotator. Okay. So, half wave plate can be used as a polarization rotator. You put a half wave plate between 2 crossed polarizers. Okay. So, it is a vertical polarization is coming in, you go through a half wave plate at 45 degrees, that vertical polarization will become horizontal polarization, right, and that horizontal polarization now can go through the analyzer. So, you can actually rotate the polarization using a half wave plate. So, quarter wave plate is used to convert linear to circular polarization, half wave plate is used to rotate linear polarization. So, I mean if you consider theta equals to 45 degrees, that is the easiest example, right. If you say 45 degrees, then this will be the mirror image of that along the y axis. So, you will find that that corresponds to a 90 degree rotation. Okay. So, that's what we are talking about. So, we are out of time, so let us stop here.